Hey guys, in this video I'm going to demonstrate a bandpass filter, how it's built, and what you can expect to see on the oscilloscope for the output of a bandpass filter. So this is the bandpass filter that is built on the breadboard. And how it's built is it's a combination of two filters, a high pass filter and a low pass filter. So how this works is the high pass filter passes all frequencies above a certain point, and the low pass filter passes through all frequencies below a certain point. So if you design it properly, so let's say you want a bandpass filter that goes from 10 kHz to 70 kHz, that has a passband of 10 kHz to 70 kHz. You would design the high pass filter so that it has a frequency cutoff point of 10 kHz, and you would design the low pass filter so that it has a frequency cutoff point of 70 kHz. So the high pass filter passes through all frequencies above 10 kHz, while the low pass filter passes through all frequencies below 70 kHz, and that's how you get the passband. So this right here is the characteristics curve of a bandpass filter. So all frequency outside of this region is referred to as the passband. These are the frequencies that get passed through the output with full gain in this region, and frequencies outside the passband are frequencies that are greatly reduced or attenuated. This is a characteristics curve of gain versus frequency. So outside of the passband, the signal gets passed through with very low gain. And yeah, this region is referred to as the stop band. It's right here and right here, while this frequency range, this range is referred to as the passband. So we designed the high pass filter to form the lower cutoff frequency point, and the low pass filter to form the upper cutoff frequency point. So the high pass filter passes through all frequencies if I'm using 10 kHz, above 10 kHz, while the low pass filter passes through all frequencies below 70 kHz, and that's how you get that sandwich effect. And this creates the passband for the bandpass filter circuit. And how you calculate the cutoff points is through this formula. It's the same for both of them. So in this example, for the high pass filter circuit, I'm using a 10 nanofarad capacitor and a 1.5 k-ohm resistor. And plugging this into the formula, I get a cutoff frequency point of about 10.6 kHz, which is approximately 10 kHz, which you can roughly say is 10 kHz. And then for the low pass filter, I use a 2.2 k-ohm resistor and a 1 nanofarad capacitor, and that creates a frequency of about 72.3 kHz, which you can roughly say 70 kHz. So the passband for this circuit with these values that I chose is approximately 10 kHz to 70 kHz. So these are the frequencies you'll see pass through with with full gain, and outside of this the passband, you'll see that the signals are greatly attenuated, and the farther you get away from the passband, the more it's attenuated. So right now I'll demonstrate this. So this is the circuit right here. This is the high pass filter, this capacitor and this resistor. Then I have another resistor and a capacitor, and that forms the low pass filter. So right now the function generator is set, so it's at about it's fluctuating between 1 and 2 kHz, which is well outside the passband. So again, for this circuit, it's 10 kHz to around 70 kHz. So as I increase the frequency, you can see how the signal is getting more gain. Now I'm at 7 kHz. I'm at 8 kHz, and you can see how the signal has increased. So now at 12 kHz, I'm well in the passband. So let me just adjust this so you can see it better. I'm well within the passband. So 20 kHz, You can see the frequency is increasing as I've increased it, of course, but the gain is staying constant. And this is because I'm in this region where the gain is constant. This is the region where the frequencies are getting through with full gain. So this is why you can see the frequency is increasing but the gain is unchanged. So right now I'm at 33 kHz, 40 kHz. And as I keep increasing it, let me have to adjust this. Okay, so let me just start again. So right now I'm at 40 kHz, 45, and then you can see now I'm outside the passband. So as I get farther and farther away, there's more and more attenuation. And if I increase the frequency to now it's at 15 megahertz, you don't see anything at all. So I'm well outside the passband. So this is here. So if you look at this point, it's well outside the passband, and so the gain is, if you look on the graph, it's practically nothing. And this is why you can't see anything on the oscilloscope. So this is how a bandpass filter circuit works. You can design the bandpass filter so it has any lower cutoff frequency point or upper cutoff frequency point, and you can adjust this by changing the values of the resistors and the capacitors in the low pass filter or the high pass filter. And this is how a bandpass filter circuit works.